Greetings to everyone. I am Aman Kumar, pursuing BTech from Faculty of Engineering at the University of Lucknow, and today I am honored to present my seminar on the topic of earthquake early warning system. This presentation is structured into several sections beginning with an introduction to earthquake, the importance of earthquake early warning system, and their working principles. Next, we will explore the science behind the earthquake detection, the technologies involved, and the example of global implementation. Finally, we will analyze challenges, future, direction, and two case studies. Let's start with understanding the earthquakes. In this slide, we will get to know about what is an earthquake, why earthquake early warning systems are essential, and what are its key benefits. An earthquake occurs when two blocks of earth crust suddenly slip past each other along a fault. The focus or hypocenter is the point below the surface where the earthquake starts, while the epicenter is directly above it on the surface. Earthquake early warning system or EEWS are designed to detect primary seismic waves or P waves, which travel faster but cause minimal damage. These systems issue alert before secondary waves or S wave arrives, which are slower but more destructive. EEWS are essential due to the significant impact of earthquakes globally between 1998 and 2017. Over 750,000 lives were lost to earthquakes, accounting for total 60% of all disaster-related fatalities. The economic losses from such events run into billions of dollars, disrupting economies and livelihoods. The benefit of EEWS include life-saving alerts that provide time to drop, cover and hold on, automatic shutdown of trains, gas lines and power system to protect infrastructure, economic safeguard by minimizing damage and aiding business continuity, faster emergency response through preemptive development of resources, community resilience by lowering anxiety and advancing seismic research. In this slide, we will know about how earthquake early warning system works. Earthquake early warning system operate by detecting P waves using a network of seismometers. These are less destructive waves that travel faster than the secondary waves. The process involves analyzing real-time seismic data to estimate earthquake's location, magnitude, and intensity. Alerts are then transmitted through multiple channels such as smartphone, television, radio broadcast, and public sirens. The warning time depends on the distance from the epicenter and can range from few seconds to over a minute, giving communities crucial time to respond. The science behind detection of earthquake is that seismometers are instruments that measure ground motion. They detect different types of seismic waves, primary waves or P waves, which cause rapid compression and expansion of the ground. These are the fastest waves but cause minimal damage. Secondary waves or S waves, which cause side to side or up and down motion. These are the slower but more destructive. Surface waves, which travel along the Earth's surface and cause the most significant ground shaking and destruction. Understanding the motion and timing of these waves is crucial for effective early warnings. In this slide, we will discuss about how primary waves and secondary waves works and their movement. Primary waves are the fastest seismic waves that travel at a speed of 6 to 7 km per second and have a motion of compression and expansion in the direction of travel, while secondary waves are slower than P waves and travel with a speed of 3 to 4.5 km per second. They can only pass through solids and they are more destructive in nature. Several agencies are responsible for managing and implementing earthquake early warning system. In India, the National Disaster Management Authority (NDMA) and IIT Roorkee lead efforts to monitor seismic activity and disseminate alerts. In Japan, the Meteorological Agency (JMA) manages one of the most sophisticated earthquake early warning system, utilizing extensive seismic networks like HyNet and KNet. These organizations are essential for deploying sensor, analyzing data, and ensuring timely alerts. In this slide, we will know about how sensor detect seismic activity. Sensors like pendulum seismometers measure ground motion by tracking the relative movement of a suspended mass. Other advanced technologies include electromagnetic sensor which generate voltage based on ground velocity, piezoelectric sensor which convert pressure changes into electrical signals, fiber optic sensor which detects seismic activity through changes in light transmission. This data is transmitted to a processing center for real-time analysis where amplitude of waves, intensity, arrival times, helps in triangulating location, and magnitude were analyzed, enabling early warnings. The key components of an earthquake early warning system include seismic sensors to detect ground motion with high sensitivity, data processing centers where seismic data is analyzed, communication systems to deliver alerts via mobile apps, TV, broadcast, and sirens, user terminals, devices, and apps that receive alerts for individual and organization. Earthquake early warning system leverage cutting-edge technologies like seismology to develop accurate models for earthquake detection, machine learning to reduce false alarms and improve prediction, Internet of Things to expand sensor network for better data collection, high-speed communication networks to ensure rapid alert dissemination. Earthquake early warning systems are classified into regional system covering large areas, often national in scope, on-site system designed to protect critical infrastructure like nuclear power plants, personal systems, smartphone apps that provide alerts to individual using device sensors. Notable implementation of earthquake early warning system include Japan J Alert integrated into public safety and infrastructure shutdowns, Mexico SASMAX providing alerts to millions especially in urban areas, the US SAC Alert covering the West Coast with a dense sensor network, Taiwan's P Alert system offering both localized and regional warnings. Despite their benefit, earthquake early warning systems face challenges like false alarms which can reduce public trust, limited warning time near the epicenter, time is often insufficient, high cost, installation and maintenance are expensive. The future of earthquake early warning system includes improved sensor and AI algorithm for enhanced accuracy, faster data processing for reduced latency, expanded coverage to include more regions and population globally. Case study number 1, Japan's earthquake early warning system. Japan's earthquake early warning system managed by the Japan Meteorological Agency is one of the most advanced globally. Japan is located in one of the most seismically active regions of the world known as Pacific Ring of Fire. Hence the development began in 1956 and accelerated after the devastating Kobe earthquake in 1995 which caused over 6,400 fatalities. By 2007, the system was officially launched nationwide with an initial network of 1,000 sensors. The system now incorporates over 5,000 sensors, including land-based and underwater installation. Japan's earthquake early warning system operate through the networks like HiNet, KNet, and MOWLAS, which monitor both land and underwater seismic activity. Advanced algorithms like integrated particle filter IPF and propagation of local undamped motion plumb enhance accuracy, particularly for near field earthquakes are used. An initial investment of 10 billion yen and an annual budget of 5 billion yen ensure its continuous improvement. The system offers nationwide coverage including urban areas and remote regions, making it one of the most comprehensive in the world. Due to continuous improvement and ongoing development, the system's overall hit rate for predicting seismic events is generally above 85%, particularly for earthquake with a seismic intensity of 4 or higher on GMA scale. During the 2011 Tohoku earthquake, the system provided 15 to 80 seconds of warning, enabling critical infrastructure shutdown and saving lives. In 2022, it issued a 30-second warning during the Fukushima earthquake, proving its reliability in offshore events. In the 2011 Tohoku earthquake, warnings allowed bullet trains to halt and industrial machinery to shut down, minimizing damage and casualties. And in 2022 Fukushima earthquake, a 30-second warning was provided, showcasing the system's efficiency in offshore events. Challenges and future enhancement. Despite a high accuracy rate, there are challenges with false alarms and reduced warning times for earthquake with epicenters near urban areas. Public response to alert is still an area for improvement, as studies suggest only around 7% of people immediately take protective actions upon receiving results. Japan's plans to invest in next generation sensors and AI based predictive algorithms to further increase the system's accuracy and reduce false positives. Expansion of international collaboration to establish the regional seismic network with neighboring countries like Taiwan and South Korea, enhancing transnational early warning capabilities. Global influence include inspiration for other nations. Japan's earthquake early warning system has set a global benchmark, inspiring similar earthquake early warning system in other countries like Mexico SASMAX, Taiwan P-Alert system, and the United States SHAKE Alert. In conclusion, Japan's earthquake early warning systems exemplifies the nation's commitment to disaster resilience. The continuous investment in technology and infrastructure improvement has made the earthquake early warning system an indispensable tool in safeguarding lives and minimizing earthquake related damage. This is the second case study on Uttarakhand, India earthquake early warning system. In India, the Uttarakhand earthquake early warning system was developed by IIT Roorkee in collaboration with Ministry of Earth Sciences. Launched in 2015 with a budget of Rs 50 crore, it focuses on seismically active regions in Uttarakhand. The system includes 170 sensors strategically placed across the state, covering regions prone to earthquake in seismic zones 4th and 5th. Sensors deployed in Uttarakhand covers the area from Joshimath to Mori in the west, and later it got expanded to Kumaon region with additional installment of 86 sensors, making a total of 170 sensors, and interspacing provided between each sensor is ranging from 10 to 20 km to provide wider area coverage of 150 by 50 km of area. Sites selected for the installation of these sensors are BSNL and Swan building due to availability of consistent power supply, secured facility, dedicated virtual private network connectivity. These are the sensor location in the Uttarakhand region of the earthquake prone Himalayan region. The site chosen for installation are BSNL and Swan point of presence buildings. The Bhukamp Alert app was introduced in 2021 to disseminate real-time alerts via push notification and SMS. It has been widely adopted with over 1 million downloads, providing life-saving warning to residents. Data is transmitted via GSM/GPRS and satellite communication to IIT's Roorkee Central Monitoring Station. The system provides alert within 2 to 5 seconds of detecting P waves, offering up to 1 minute of lead time based on distance. It can detect earthquakes with a magnitude of 5 or higher on a Richter scale and issue a warning, while warnings are issued for earthquakes with a magnitude exceeding 5, while notifications are dispatched for those below magnitude 5. Achievements of Uttarakhand earthquake early warning system are: as on 8 February 2020, it detected Pithoragarh earthquake of magnitude 4.7 on Richter scale, but it was marked for research purpose only and had not been revealed to the public. In this slide, a graphic user interface of the Uttarakhand Bhukamp Alert app, which will send a notification of earthquake in advance with its location, magnitude, and will provide a SOS button stating I am safe or I need help, and user have to select anyone. If they need help, they will select the option accordingly and the response team will be diverted to their location. It also provides safety measures for people like covering their head, getting out of the basement quickly, etc. Both the earthquake Chamoli and Tehri Garhwal were successfully detected by earthquake early warning system, and users were notified through mobile app. In case of Tehri Garhwal earthquake, the Artola station was 166 km away from the epicenter. Hence, there was a lead time of approximately 38 seconds for the ARTB station before the arrival of destructive waves, which took approximately 50 seconds from the origin time to reach the station. The system generated 6 reports and recorded data from 96 stations, showcasing its dense instrumentation and rapid response. Notifications were successfully sent to the public users through the mobile app from the third generated report onward. Since 2015, the system has produced reports for 19 earthquakes, of which 14 occurred in the Uttarakhand region, 5 occurred in Nepal. Automated response system, automatic shutdowns of power plant, elevator, gas lines to prevent secondary disaster are not yet implemented as compared to Japan earthquake early warning system. Despite its success, Uttarakhand earthquake early warning system faces challenges like difficult terrain, complicated sensor placement and maintenance, communication disruption from landslide, weather, and power outages hinder real-time alerts. Public adherence to warnings remains low, highlighting the need for greater awareness and education. The Uttarakhand system plans to expand coverage to other seismic zones like Himachal Pradesh and the Northeast, integrate artificial intelligence and Internet of Things to enhance accuracy and speed, explore alternative power solutions like solar backups, and use public networks for resilient communication. These advancements will improve the system's reliability and accessibility, making it a model for other regions. In conclusion, earthquake early warning systems are indispensable tool for disaster resilience. Japan's earthquake early warning system, with its extensive sensor network and automation capabilities, it exemplifies how technology can protect lives and infrastructure on a national scale. Uttarakhand's earthquake early warning system, it is a localized approach and an innovative use of mobile apps, demonstrate how effective solution can be tailored to a specific needs and budgets. Both systems highlight the potential of earthquake early warning system to save lives and minimize damage. Continued investment and innovation will ensure these systems remain at the forefront of earthquake preparedness. All information presented in this presentation has been sourced from reputable academic journals, industry reports, and authoritative text on earthquake early warning system. The references used have been carefully selected to ensure the accuracy, reliability of the data presented. A full list of reference is given below. Thank you for your time and attention. The earthquake early warning system represents a crucial advancement in disaster preparedness and risk mitigation. By embracing this technology, we can save lives, protect infrastructure, and enhance community resilience. Your support and interest in this vital topic are greatly appreciated. Thank you.